This is lesson 7.2, Arcs and Chords, Unit 7 Circles. Make note of both the date, time, and location that you are watching this, as well as don't forget a parent, guardian, or teacher sign-off. Let's do a review problem. Last class we talked about these words, diameter and radii. Diameter and radii. We're going to use those in solving this problem. It says, in the circle above, the diameters, which is from edge to edge of circle A, circle B, and circle C are 10 centimeters, 20 centimeters, and 14 centimeters, respectively. Find all possible segments. So let's draw that in. Diameter goes from edge to edge through the middle of a circle. So A, our diameter, is 10, which means that the edges here are going to be 5 and 5. That's the radii. And then the middle one is a 20. So from this edge to this edge, right here, is 20. And that would make this from here to here a 10 and a 10. And the last one is 14. And that's C, so that's from this edge to this edge is 14. Find all possible segments. The easiest way to find all possible segments is to bracket the possible segments. So let's bracket one of them. BY is a segment that is not found. Let's bracket what's around it. We know B to C is 10, and we know Y to C is 7. I'd like you to find B to Y, the red there. Go ahead and find it. Okay, you should have gotten 3 there. Another one that we don't have is X to B. X to B we don't have. I'd like you to attempt to find X to B. Bracket what we do have and see if you can't find that. You should have gotten 5. Why? Because this is 10 and that's 5. You simply physically bracket what you do have and bracket what you don't have. It'll be very easy to work this out. Okay, let's see what we're focusing in on today. Your vocabulary today, we're going to be talking, of course, about circles, chords, how chords and arcs interact, the concept of distance, congruent, and of course, the infamous right triangle. It says right here, draw in 2 congruent chords, then sweep the corresponding minor arcs. So 2 congruent chords. Make them hatch marks. Those are of congruent length. Now sweep the arcs. And what you're going to notice is if you have congruent chords, you have congruent minor arcs, the corresponding minor arcs. If you have congruent chords, you have congruent arcs. The converse is also true. If you have congruent arcs, you have congruent chords. Because it's true, both the conditional and the converse is true, we call this biconditional. It's a biconditional statement, and we can write it like this. Congruent chords, congruent arcs, and you do a double arrow, which means it's true both ways. Okay, now we're going to get into a concept called distance. In a circle, distance from the center is a very particular term. Distance from the center implies two things, actually three. Distance in a circle is a segment. That's the first thing you should realize. It's a segment. Two, it's a perpendicular segment. It creates a right angle. Three, it's a bisector. So what that means is in this circle, we know that we have congruent chords. BE, notice the hatch mark is congruent to CE. Now if the chords are congruent, the distance from the center, remember that from the center is a segment, so we're going to draw in a segment. It's going to bisect the chord and is perpendicular to the chord. So there's your midpoints. From the center is that right there is from the center distance, and that right there. And it does two things. One, the distance from the center creates a right angle. Two, the distance from the center bisects the chords. So these two red segments are what would be called distance from the center. Those distance segments also bisect and are perpendicular to the chord. For the next segment, you're going to need a ruler and a straight. You're going to need a straight edge of some sort. So, if necessary, pause the video and go get a straight edge. It says trace and sweep EHF. Let's do that. EHF. It says draw on a radius HI, which is also the bisector of EHF. So we're going to draw an HI. There's going to be I, and it's going to be a bisector of that original angle. Now we're going to draw in the chord EF. So E to F, this is where I'd like you to get a straight edge. You're going to draw in the chord. Now I'd like you to trace that chord, trace the chord, and I'd like you to trace the radius HI. And I'd like you to take a moment, and if you need to, do it again. I'd like you to trace both those, EF and HI again, the radius and the chord, and I'd like you to write down what kind of things do you feel, what do you notice there as you trace? What do you notice? Take a moment and write that down yourself. What do you notice? There's two things you should notice here. Actually, three. That radius that bisects the angle also bisects that chord. It goes through the middle of the chord. It bisects, the radius bisects the angle and bisects the chord. And if you notice, as it bisects, it also makes a right angle. So the radius that bisects that central angle is both bisects the chord and makes a right angle. Those are the two things you should have noticed. Go ahead and draw those in. Makes a right angle and bisects. Which leads us to our most important concept. of this lesson. I'd like you to draw in the center of the circle. I'd like you to use a straight edge and draw a chord. We're going to bring this really close here. Draw a chord. Now, I'd like you to draw a radius perpendicular to the chord. A radius perpendicular to the chord. Make the right angle. Okay, so what we have here is if a radius is perpendicular to a chord. If a radius is perpendicular to a chord. Write that down, please. You should notice that it also, if it's perpendicular to the chord, it actually cuts that chord in half. Or in other words, then the radius bisects the chord. Let's boil it down to the essential words. If perpendicular, then bisect. If perpendicular, then bisect. If perpendicular, then bisect. Converse is also true. Let's draw this one here. I'd like you to draw in a radius, or draw a chord first. Now I'd like you to draw a radius that bisects the chord. So eyeball that chord's middle and put hatch marks there. Now, draw on your radius through the center of the chord. You should notice that the converse is also true. If a radius bisects a chord, it's also automatically perpendicular to the chord. So the first, if perpendicular, then bisects is true. The second is also true. If bisect, then perpendicular. If bisect, then perpendicular. If the radius bisects the chord, it's also perpendicular to the chord. This is the most essential concept of this particular lesson. Let's see how we can apply this. We're going to take these bullets one step at a time. Step number one, it says, in the circle below, label the center P. Now I'm going to do this in different colors. So let's start with something simple. There's the center. We're going to label it P. Do a little check. We're going to draw a radius PQ, and we're going to make that radius 13 centimeters. So we're going to draw a radius PQ. We're going to make that radius 13 centimeters. Now we're going to draw a chord JK, which is 5 centimeters from the center. We're going to draw a chord JK, which is 5 centimeters from the center. I'm going to be very specific about my colors here. So JK is going to be 5 centimeters from the center. So here's JK. 5 centimeters from the center. Remember, from the center is code for a segment which hits the midpoint, so hatch marks, and makes a right angle. So that is from the center 5 centimeters. Next one says we're going to draw in another chord which is congruent to JK. So AB and JK are going to be the same length, but AB is going to be bisected by the radius PQ. So AB is going to be cut in half by that radius PQ. Here's AB, cut in half by the radius PQ. Now you learn that if perpendicular, then bisect. And if bisect, then also perpendicular. So we're going to put in a right angle. And we also learned that if two segments are congruent, two chords specifically, if the chords are congruent, then the distances are also congruent. So if this distance here is 5, this distance here is 5. I'm going to bring this around so you can see it. 5 centimeters. Now it says we're going to find everything possible. One key thought here is when you find everything possible, you can always add, move, or draw in radii. You can always add, move, or draw in extra radii. And the reason why is because all radii are congruent. So let's see what we can figure out here. Bring this nice and close now. Well, let's see what we do have. We have 5 here, and we know this whole thing is 13. Let's bracket from here to here is 13. Remember I told you that right triangles are the key to the universe? Because right triangles are so critical, if you ever have an opportunity to make a right triangle, you should take advantage of that. For example, let me give you one example here. We have a right angle here, so you want to look for a way to make a right triangle, which I'm going to do here. From here to here, we're going to connect, and we're going to create a right triangle, and let's see what we can find here. So I just drew in an extra radii, and now, because I drew that in, I have a right triangle. Take a moment and shade that right triangle. Because we know all radii are congruent, I'd like you to bracket this 13. I'd like you to swing it around and bracket from here to here. You should feel, again, bracket, bracket. Take your pencil, bracket Q to P. Bracket here, A to P, you should feel that that is the same, because all radii are equal, so that's 13. So now look what we can do here. We have a 13 centimeters. We have a 5 centimeters. And we don't know this piece here. We're going to call it X. You should recognize that we have a right triangle here, 2 sides, so we're going to use leg squared plus leg squared equals hypo squared. Write that down. Let's circle plug chug. Leg, leg, 5 squared plus other leg, you don't know it, squared, equals hypo, hypo, 13 squared. Let's solve. We have 25 plus x squared equals 169 minus 25 both sides. We end up with x squared equals 144. And we square root both sides, and of course we get x equals 12. Let's bring that around here. That means A to this point is 12. But because if perpendicular then bisects, this is 12 over here. 12 and 12, which gives us the length J to K, which is 2 times 12, is 24. Now when I say all possible segments, don't overlook something simple like this. 13 is here, 13 is here, and we have 5 here. That means from here to here is going to be 13 minus 5. Which of course is 8, that light blue. Now we have found everything possible in the diagram. Take a moment, make sure you have all that work down in detail. Let's try one more problem together, and then you're going to do one on your own. So I'm going to do one of the you try problems with you. Let's take a look at what we have here. The trick to solving these is just to physically trace stuff out, get a feel for the diagram. So let's see what we have here. We have a radius, trace it please. And we have a chord, trace it please. And we have a right angle. And we learned that if a radius is perpendicular to a chord, then it bisects. If perpendicular, then bisects. Put in your hatch marks. Obviously, we have found 6 already. If this is 6, that's 6. And if the radius is perpendicular to the chord and bisects the chord, it also bisects this arc, which means if that's 75, this y is also 75 degrees. Now you're going to do one problem completely by yourself. I'm going to set the timer for 2 minutes, and you are going to solve, find, and do everything you can to solve for what's being asked for in this diagram. Ready? 2 minutes on your own. Go. Okay, let's see how you did here. We were told in this diagram that BD is 12. So let's trace B to D is 12. and A to C is 3. We're supposed to find the radius and the measure of arc B to D. Well, let's first find the radius. Our radius is right here, B to A. Let's start with something simple. If this is 12, we can mark this out as 6 and 6. Why? Because if perpendicular, then bisect. And we have, once again, a right triangle. Let's pull this out so you can see it. This is 3, this is 6, this is x. Let's see what we can find. We can do leg squared plus leg squared equals hypo squared. Circle, plug, chug. Our first leg is 6 squared plus 3 squared equals our unknown x squared this time. We have 36 plus 9 equals x squared. That's 45 equals x squared, and then we square root both sides. There's two ways we can do this. We can factor it out, and we end up with 5 times 9, and then 3 and 3. So you pull out the date, we have 3 root 5. Or we can just go square root of 45 since I don't specify, and we get 6.7. If I had specified simplified radical form, I would have won 3 root 5 here. Now notice, we also want the arc B to D, the measure of the arc. Now the trick to this is we need to pull this out, and we need to find this angle right here, BA, and then I'm going to add a point here. We're just going to call that x. That angle is the same as this angle right here. Now I'm going to call that x. The x degree angle. Now to find this angle, we're going to use inverse SOHCAHTOA. So I'm going to work with the 6, which is the opposite, and the 3, which is the adjacent. And that gives me OA, and I'm going to use tangent. So I'm going to use inverse tan. Opposite over adjacent gives me the angle. I'm going to pause. If you haven't done that, you want to write this down. So we're going to use inverse tangent, opposite over adjacent. So on your calculators, many of you are going to do second function tan, 6 divided by 3. My calculator goes the other way. I go 6 divided by 3. Then I do inverse. Notice that's going to give me tan negative 1. And I get 63 degrees. So my degree measure here is 63 degrees, which gives me 63 degrees here. We know measure of a central angle to its arc the same, that's 63 degrees. And if perpendicular, it bisects the arc, so if that's 63, this is 63. And you should be able to now trace the arc B to D. Can you pause and trace that if you haven't done so already? So in this case, the measure of the arc B to D is going to be 2 times 63, which is 126 degrees.